Welcome back, everyone. Let's get right into today's explainer module, where we are going to completely deconstruct Pi. Now, if you're studying advanced computer science and modern software architecture, understanding how autonomous coding tools integrate safely and efficiently into existing workflows is absolutely paramount. Today, we aren't just looking at another AI wrapper. No way. We are dissecting a fundamentally new paradigm in systems design, a first principles agentic coding harness built for enterprise-grade workspace automation.
Here is our syllabus for today. We're going to cover 1. The agent harness paradigm, 2. Monorepo and supply chain hardening, 3. Core state machine operations, 4. Persistence, branching, and compaction, and finally, 5. Virtualization and security sandboxing. All right, let's jump right in.
Section 1. The Agent Harness Paradigm. Let's establish our conceptual framework.
So there is a massive philosophical shift happening in the industry right now, and you need to pay attention to it. We're moving away from the rigid, monolithic agent orchestrators of the past and shifting toward highly flexible, command-line integrated utilities. Traditional systems, well, they kind of force you into their predefined master planners and nested abstractions. They trap you in their specific way of working. Pi, on the other hand, is built strictly as a terminal-first harness. It doesn't force a workflow on you. It adapts to yours by keeping the core loop minimal and pushing all that rich customization straight to the edges.
And the crucial definition to take away here is this: drawing deep inspiration from the traditional software test harness. You know, the kind that automates execution and mocks dependencies. Pi just manages the core loop. It handles reading, writing, and executing shell commands. You bring the logic. By shifting custom workflows and guardrails to a programmable extension layer, it gives you the ultimate freedom to shape the tool to your exact engineering requirements. It's a real game changer.
Section 2. Monorepo and supply chain hardening. Let's examine the architectural taxonomy of its monorepo and, more importantly, how it secures the software supply chain.
Look at how these decoupled TypeScript packages, maintained under the ArundelWorks organization, are structured. As computer scientists, you should instantly appreciate this separation of concerns. Notice how the core language model interactions in Pi AI and the agent run loop in Pi Agent Core are strictly isolated from terminal rendering in Pi TUI and file system operations. Because of this beautifully decoupled architecture, enterprise developers can consume individual modules in entirely non-terminal runtimes, like custom web dashboards, without dragging in a bunch of unnecessary dependencies. Now, because Pi executes generated shell commands locally on your machine, ArundelWorks implements a rigorous security checklist. They have to mitigate potential same-day supply chain attacks. In modern software engineering, we all know you simply cannot blindly trust downstream registries, right? One compromised package can literally nuke your entire infrastructure. So Pi enforces a 48-hour minimum release age for external dependencies, shielding you from immediate package takeovers. On top of that, execution isolation completely blocks unauthorized build steps by enforcing npm CI ignore scripts in CI workflows. Honestly, it's a masterclass in hermetic, secure software distribution.
Section 3. Core State Machine Operations. Let's trace the execution lifecycle and check out the dynamic state machine.
To serve as a truly foundational tool, Pi supports multiple modes of execution. You aren't just locked into one interface. The execution modes range from raw keystrokes in the interactive TUI for local diagnostics to programmatic JSON event logging, all the way to bidirectional JSON-L streams over standard streams in RPC mode for building IDE plugins. There's even a native Node.js SDK for seamless in-process automation workflows. It covers the whole shebang.
Now, what is truly fascinating to me is how Pi completely avoids freezing execution during model runs. Traditional multi-agent architectures block you until all nested tasks resolve, which, let's be honest, is incredibly frustrating. Pi maintains distinct non-blocking queue channels. If the model is executing a tool and you notice it's going down the wrong path, you can just inject a steering message by hitting enter. The engine will actually interrupt any planned tool calls right after the current one finishes, forcing the model to instantly reevaluate its path based on your real-time human guidance.
And to support the absolute bleeding edge of advanced reasoning models, Pi's translation layer maps structured thinking levels directly to provider-specific token budgets. So, whether you're assigning a low budget for basic code review or an X-high allocation for massive structural software design tasks, the harness dynamically translates those intentions into native API parameters. It entirely abstracts away the headache of managing different provider protocols.
Section 4. Persistence, branching, and compaction. As an agent session branches infinitely, how do we actually handle memory persistence and context constraints?
Well, instead of a linear history,
Pi serializes human conversations as immutable tree structures inside flat JSON-L files. Think of it exactly like a Git version control tree, but for your AI conversation. Every single line is an event with a transaction ID and a parent locator. This allows you to execute completely non-destructive commands like /fork or /clone. You can test a highly risky script refactor on a separate branch, and if it completely fails, no problem. Just roll back to the parent node and try again without polluting your primary workspace history.
But this brings us to a really critical architectural challenge we have to address in this module: handling the physical token limitations of large language models. Infinite trees mean infinite tokens, which models simply cannot process. So what does this all mean for memory management?
To solve this bottleneck, Pi executes a highly specific multi-tiered compaction sequence. When it estimates the token utilization is getting too high, it scans backward from a target cut point to find a boundary immediately before a user message. Why do it that way? To ensure that tool results are never orphaned from their corresponding assistant instructions. Furthermore, notice that last step, the compaction guard. This is a mechanism that halts the summarization entirely if no valid messages are eligible. It completely prevents the disastrous scenario of sending a blank summary to the model and wiping out its working memory. Because yeah, giving your AI an incurable case of amnesia is definitely not best practice.
Section 5, Virtualization and Security Sandboxing. Okay, so if the model is operating safely within its token budget, how do we ensure the generated code executes safely on your physical machine? Let's talk virtualization.
Enter Gondolin. This is Pi's specialized virtualization engine, designed specifically from the ground up to run untrusted agent actions. Instead of some heavy overhead, Gondolin spins up a super lightweight 200 megabyte Alpine Linux guest VM managed by a TypeScript control plane. On Linux, it runs entirely in user space via KVM. No root privileges required. On macOS, it seamlessly taps into Apple's native hypervisor framework. It is incredibly fast, and it is entirely isolated. When we compare containerization profiles, Gondolin's true power becomes super obvious. While plain Docker often requires passing keys directly into the container and bind mounting files, which can get messy, Gondolin perfectly confines tasks to the guest Linux VM while safely mounting the current workspace via a real FS provider. The isolation boundary here is drastically more secure for running AI-generated bash scripts than your standard container setups.
And this perfectly illustrates how Pi handles the ultimate security nightmare: managing secrets. If you give an AI access to a VM, you absolutely do not want your production API keys floating around in its memory. To fix this, Gondolin utilizes a host-side man-in-the-middle proxy. When the agent makes an outbound request using a placeholder, like $GitHub token, the host proxy intercepts it, checks an allow list, and dynamically injects the real credentials before forwarding it to the server. Raw security keys never ever enter the guest VM's memory space. It's brilliant.
Which brings us to the underlying philosophy of Pi, and perhaps the most important concept in today's curriculum. We are moving away from software as a static artifact. Because of Pi's highly extensible architecture, with its async factories and custom UI registries, you can actually instruct the AI agent to rewrite its own underlying extension files in real time. It can add a custom tool, run a /reload command, and instantly continue execution with its newly acquired capabilities. It is a dynamic, self-modifying system tailored to your exact workflow.
So, I will leave you with this final thought to ponder as you master the concepts covered in today's explainer. As agentic harnesses evolve to rewrite their own underlying extensions and architecture in real time, what does the future of the human software engineer actually look like? When our tools can safely branch their own logic, securely sandbox their executions, and dynamically rewrite their own capabilities on the fly, our role shifts dramatically from syntax generators to architectural directors. Study these first principles well, students, because this harness paradigm is exactly where the industry is heading. Keep questioning, keep building, and I will see you all in the next module.